funny.
Oh, look at the best! She's the best!
How is Taekwondo Canadian?
Sorry, the last one how like
Crap.
she's little and so she has to like blah blah blah. It's okay. You know those things sometimes happen.
But how is Taekwondo Canadian? It's Canadian heritage. Taekwondo is like
She
Chinese.
explained it. No, she explained it all to me, but I didn't really listen because she was
cute.
there.
Oh,
Taekwondo ain't Canadian.
It's
yes,
in
it is.
Canada.
It's
Totally Canadian, don't you know? She said that
Everything's in
when
Canada.
you taught some of the war veterans Canadian Taekwondo, and then they could beat up people and something like that. And then they could beat up people.
She just said it wasn't.
I think
Taekwondo,
she
it's
might be on
karate.
track.
Do you have like a
Who was it?
You're taking scrub.
Oh, they hung you up?
Talking pairs too.
On your room?
She has like a. Does anybody know her?
Yeah.
Because you're a black belt, Sam, so you can kick James.
Actually no, because he could bench press me with one arm, so. And then when she tries to come his weight, she shut up.
Well, isn't he like
Let's
two-
not bring up that.
Are you doing like a
Probably
lab
about
on this
220.
when we get back?
Yeah.
No.
It's just really inconvenient timing where Easter break is.
200 on the dot.
That's what Josie said too.
Yeah.
Really messy.
It's just
Maybe
not
it wasn't 200 when
ideal.
you graduated, though.
Because I'd like to do a hands-on experiment, but I really shouldn't do the experiment until after this lesson, but so be it. Okay, let's talk our last lesson, then we're done for the
I called it.
Easter
eh?
break. Called what?
This small.
We have a lot of kids still. We have 11.
Yeah, we have
How many kids are in your class?
I don't know. I should probably know, but I don't.
Missing
Let's see who we're missing. We're missing Conlon, Jack, Kayla.
Where's Kayla? She
Nicole.
was here.
She went home.
Kayla.
She went to Tinch.
We're only
I
missing
don't
like
think
5
Nicole was
people.
feeling very well.
Alright, so 4 missing,
Jessica.
5 missing, Jessica.
Anyways, we got the faithful ones.
You guys are here.
Yeah.
And then
I
Easter.
printed them.
Okay. Nope. I just locked door there. We have one more.
Oh, maybe we're getting one back.
Hello?
Cello?
No, no.
There we go. Now we're only missing 4. Perfect. Okay, let's talk about just a generic battery cell. Okay. I don't actually care what it's made out of, so why don't you guys give me 2 electrodes, just 2 different metals we can make it with. Nickel and copper, I heard. We'll go with that. So I don't actually care which one is which, so let's go with this one is nickel, and this one is copper. It's really irrelevant which way they go. It's up to you.
I'm writing it.
I'm not.
Do you want me to give you a second just to draw a picture first? Okay, I will put my board down and sit.
Is this kind of how it goes back and forth? Or like how it charges?
We're just let me teach. I'll get to it. I promise. I have a point.
KNO3 is the salt.
Yeah, that's what I was going with. KNO3 is usually the salt bridge because potassium is as low on the list as you can get. K plus, like it is like the weakest oxidizing agent that we know of. I think maybe sodium is lower, but like potassium is about as low as it gets. Or lithium is lower, maybe. Yeah. And then nitrate we often like to use because as a negative ion, nitrate's not on the table unless it's with H plus, I think.
So it doesn't influence any of the.
Exactly, yeah. So we can use it to influence charges, but it doesn't actually, like it can act as a spectator ion though.
Pretty much KNO3 is just there to be a weak oxidizing agent.
Well, it's not there to do the oxidizing or reducing, it's there to help keep the cell running due to positives and negatives needing to move. You guys good? Can I keep going? Okay. Typically what you're going to do then in a cell, and this is not always what you do, but typically if this is a nickel electrode, we would put nickel 2 plus in this particular electrolyte. That's typically what you do. And then if this was a copper electrode, typically you'd put copper 2 plus in this particular electrode. Okay. So let's try to figure out what would happen in the cell now. So if you were to have, like, say, a data booklet page nearby. I don't have one nearby. I'll just have to pretend that I have one nearby. I'm pretty sure that the way it works is that copper is about in the middle of the page. And then nickel is a little ways lower than it, but not like crazy much lower, but a little lower. let's say I asked you to find the voltage of this battery, like how many volts it can provide. What's copper's value?
0.34.
Okay. And nickel is?
-0.26.
Okay, now in terms of working this formula, what should happen then is this copper 2 plus should go this direction. And this nickel solid should go this direction.
The copper 2 cathode.
Okay, so let's write this out then. So it means that,
Why you just,
okay,
why?
so this is going to react with this because it's spontaneous. So that means this guy is going to have to turn into this one, and this one is going to turn into this one.
Fill in the blanks.
Carla?
With the electric potential stuff, if you flip your equation, does that mean you're flipping your voltage? Ever? Because I saw that in the notes and it kind of confused me. With
No, I would say as a general rule, the best way of doing it is we probably shouldn't do that. Because what you want to do is you want to take this, how do I put this here? Your data table is written as though everything is doing reduction. If you were to write your entire data table as though everything was doing oxidation, all of these numbers would then flip. But it's usually best just to take your cathode and your anode numbers and subtract them as though they were both reduction numbers on the table.
Okay. Even though technically the nickel
Is going the other way here.
Okay.
So, I mean, I guess what you could do is then you could say what you have is 0.34, and then what you're going to do is you're going to add 0.26, because then you're really flipping this to become a positive number, and you're adding the two of them.
So,
It's easy. It's just easiest in general to say take your top number, subtract your bottom number, which then means our total voltage would be 0.60 volts.
okay, do you know how sometimes you can manipulate your equations and
Like times them by 2 or 3 or something?
Why don't you change your voltage to?
Okay, that's actually a good talking point. I was going to do this at some point. I'll do it now. I want to talk a bit about what voltage is. Okay, voltage, if you guys are in my physics class, and I know not everyone is, so I'm going to start at the very beginning, but voltage is defined as how much energy difference there is per Q, which happens to stand for charge. Okay. We're not going to use this in our class here, in chemistry, just so you know. So I know a couple of you guys, we've done this in physics, but I know not everyone is, so don't worry about that. But voltage is really about energy. That's the real key here, about how much energy difference you get. And the analogy that probably works best is like, imagine that you've got like one of those old like water towers. Oh, looks kind of like this. Okay.
Sorry.
You okay?
How did you do that? I was gonna say something.
Oh.
Okay.
Scared me.
Okay, let's say you put a hole in a water tower up top here. What's going to happen to this water is it's going to fall. And it's going to gain energy. Up here it has potential energy. And as the water comes through, it's going to convert that potential energy into kinetic energy. Does that make sense? Well, it's kind of a similar thing here with your battery. Over here, let's actually finish labeling it. Which one was which again? Cathode was copper, so this one is cathode, which is positive. This one is anode, which is negative. So electrons are flowing this way. Okay, so back to my energy analogy here then. These electrons right here, as they're sitting on the anode, do they have any energy yet? I would say, well, not really, I guess. Well, technically, they're probably vibrating a little bit because all matter does that, but they're waiting to move. Does that make sense? And voltage then defines out what sort of energy difference they're going to undertake as these electrons then travel from here to here. So here they have mass, they're electrons, but they have no velocity. And then as they move through the wire, their energy is going to change. Does that make sense? And so that is the definition of voltage, how much energy change there is per charge. Okay. Each of these electrons, by the way, has like one charge to it. Let me go back to this analogy. Here, the water is just sitting up here waiting to fall out. I puncture a hole in the tank. The water here has no kinetic energy, and as it comes down, it does have kinetic energy because it's moving faster and faster and faster. Does that make sense? That is what voltage is. Okay. How much energy change you have, but then it depends on how much charge you have. Because things that have, like, say, 5 electrons are different than those that have, say, 1 electron. So it's only fair to compare per charge. Okay. What we're going to talk about today is current. And current is defined as like the amount of charge you have divided by the amount of time it takes. Okay. The analogy here would be, let's say you had like a little hole punctured through here, and so water is leaking out. And let's say then you ripped a really big hole. Is the water getting any difference in energy? I would say, well, no, it's not, because the water is still going from here to here. So like in terms of energy, it's gaining the same amount of energy.
Just more amount.
Does that make sense? But like each individual drop, by the way, right? Each individual drop that comes through here, but maybe it would happen faster, because rather than it like leaking drop by drop by drop, now it's gushing out. You know what I'm saying there? And so that's what current has to do with. It has to do with how much charge you have, but it also has to do with how long it takes. I like to relate current in my mind when I'm thinking of this as like a speed. How fast are your charges moving? And so let's say the electrons move through this wire and it takes 5 minutes. Is it still spontaneous? Spontaneous just means it happens. Reaction rate is about how fast it happens. So current has to do with how fast this reaction is going to occur. So the higher the current, the faster the electrons zip from here to here. But I mean, in theory, you could have a very slow reaction where the electron is moving, it's just taking its sweet time. Make sense? Voltage, though, is based on energy differences, which, for chemistry's purposes, all we care about are what are the two species we're talking about. So we're talking about nickel, and we're talking about copper. So we have to find the two energy level differences in your data booklet, subtract them. That's how many volts a battery has. Does that make sense? Why did I get on this tangent again? Someone asked me a question.
I asked you why.
Did I answer that question in my talk there? Do you remember anymore what you originally asked?
I was asking why the ratio is. Yeah.
Thank you. Okay, so now back to the original point, now that I've gone on a big tangent here. Okay. The ratio does not matter how many electrons travel. How many electrons travel might be involved with the speed. Right? Like if you had 40,000 electrons travel versus 5 electrons travel, that might have to do with speed perhaps, but not voltage. Voltage is just the energy difference between the two. So we don't actually need to multiply by how many electrons there are when doing voltage.
Okay.
Does that make sense?
Yeah.
However, later today when I introduce the current formula, we do care about how many electrons transfer.
Okay.
Okay. So with voltage, don't times these numbers, like these numbers here, that are 34 and 26. Don't times them by 2 or 3. That's not how voltage works. Because voltage is just about energy, like mass times velocity squared, like 1/2 mv squared, kinetic energy. We don't care how many electrons move. Sorry, that was long-winded for what you wanted. This was relevant, though, because I'm going to talk about current later. So I thought I'd do it now. Let's go back to this. Where was I? Electrons are moving from nickel to copper. Are we all in agreement that that's what's going to happen? Okay, so if I keep drawing the cell, what's going to happen to your nickel anode? Is it going to stay looking like this?
No, deteriorate or erode.
Yeah, all of those words work, like deteriorate, decay, corrode, erode.
Erode means like a riverbank.
Sure. So think of like it like wasting away like a sandcastle with water. You know, like you build a nice sandcastle, the wave comes in and it comes back, it takes out your sandcastle. I don't care what word you use. Probably the best word is probably it will dissociate. That might be the best word to use. I don't care though. But often I try to draw this like this, where I'll then try to point out that this thing is going to waste away, forming more nickel 2+. Does that make sense? What's going to happen then is this beaker is going to become very positive very fast, because all of this stuff right here, all of these electrons are going to leave, leaving a bunch of positives in this beaker. Why would electrons want to leave positives? They would. That's why we need a salt bridge. Because what's going to happen in your salt bridge is the NO3s are going to start migrating this way. And you guys know the term diffusion? Like osmosis? What's going to happen is because there's a severe lack of negatives in this beaker here, the negatives are going to migrate this way from the salt bridge to keep this beaker from becoming polarized and being too positive.
So I know we're gonna look at it later, but like when I imagine a salt bridge, I can't.
We don't actually use the salt bridge, to be honest. We actually use the porous cups when I do that. So basically it's a cup inside a cup, and ions are allowed to move through it like a membrane. You guys use that term in bio?
Yeah.
What was that?
What's the point of even being in there? Remember, if things just move through.
It helps to separate it so that like one beaker is, yeah, because otherwise everything might mix a little more. I don't know that I'm describing this that well. We have to have ions move from one side to the other though, otherwise the two halves of the cell become very polarized.
Would it be, maybe this will help you understand, I don't know, but if before like the electricity or even before the reaction occurs, it's kind of at a state of like equilibrium almost, right? Because there's
Okay.
like, because the anode and the cathode are both kind of equalized still, right? But then only,
Before it starts.
so then it would, the stuff inside the porous cup would have no reason to leave, right? Is that
Okay.
kind of thing? So then as soon as the reaction takes place, then it needs.
Then stuff starts to need to move across the membrane to like,
Yeah.
I like the idea of biology, the idea of diffusion across a barrier. This is becoming very positively charged. So then negatives would then come over this direction here through this barrier. Imagine there's a barrier here, I guess, whatever it's made out of. That makes it so that the negatives can come this direction here. So that this half of your cell doesn't become too positive.
Okay.
This might help when we actually get a chance to do some hands-on stuff. I said to Carlin earlier, unfortunately, I want to do this next, but Easter break is really inconveniently placed.
Wow, like, who put that in
Every class.
It's not possible for the, obviously, NO3, like the charges on the NO3s to go through the, like all the way through again, because they're their own substance.
Well, because it's
right?
not just, it's not an electron, it's an
Right.
actual molecule now.
Okay.
Because otherwise what you're suggesting is these ones,
Yeah.
as negatives go through the wire,
That's
only
it.
electrons can flow through the wire. Okay, let's talk about this guy over here. So if the anode is going to lose mass and kind of waste away, what's going to happen at the cathode?
Build
It's
up.
gonna get bigger.
It build up, yeah. To be honest, sometimes we don't actually have to make the cathode out of copper. Because this copper itself is not what we needed to start with. We had to start with this copper 2+, which is then going to attach itself to this guy right here. So if you ever heard the term electroplating, sometimes what we do is we take a different substance here. Like one of the most famous examples is lead and gold. Rather than making, like, say, a crown out of pure gold, you make it out of mostly lead, and then on the surface, you coat it with gold. And so you think it's gold, but it's not. Does that make sense?
Back in the day, were they all gold? Just
I have no idea. I was telling Michael earlier, you guys have heard the story, I'm sure, of Archimedes trying to figure out the density of a king's crown. Mr. Orr Sr. often makes kids get into like a tank of water and have it overflow. Did you guys do this?
drown them?
You guys never done this?
No.
Okay, never mind then. This might not make as much sense. I'll tell you the story. Okay. So what he'd do is he'd get like a big garbage can full of water, right? And the question is, how much volume does a human being take up? Now, how do you determine the volume of a human being when you're so oddly shaped? So what he does instead is you fill a garbage can full of water, and you put the person in the garbage can,
Get out
and then what's going to happen is all the water in the garbage can will overflow. Measure the amount of overflowing water, that's how much volume the person has. You guys ever heard this story before? Okay, so there's a famous story like hundreds of years ago, maybe thousands of years ago. A guy named Archimedes, a famous mathematician, a king was given a new crown. But he thought maybe he was being like cheated a little bit, so he paid for a crown out of pure gold, right? But he thought maybe the guy who gave him the crown made it mostly out of lead and covered it with gold. So he wanted Archimedes to try to figure out, well, how can you tell? He doesn't want him to unmelt his crown, because then his crown is broken, right? So basically what Archimedes discovered is as he got into the bathtub, when he got into the bathtub, all of the water in the bathtub overflowed the side of the tub. And he realized he could use that to figure out how much volume the crown had, because he needed that to do his measurements. So there's a famous story about how he then ran down the street naked yelling Eureka, because he finally had solved his problem as to how to measure the volume of an irregularly shaped object. Ever heard this story?
Yes. No. You never, lab tells it in like junior high science.
Oh,
Don't remember.
don't listen to lab stories. Okay. Anyways, I've gotten off topic again. So the point of it was you could, in theory, rather than making a pure gold crown, make it with like 99% lead, cover the surface with gold, and how would you know the difference? And that's kind of what you do
Yeah,
here.
you chip it
Well,
away.
okay, but then you're breaking your crown that you just paid for.
Do it on the inside.
You're talking about gold
No, like on your head crown.
Yeah.
Okay, so back to this. The point I wanted to make here is that your cathode, I said it was made out of copper solid. But to be honest, it didn't have to be. It could have been made out of pretty much anything. Because what's happening here is the copper 2 plus is adding itself to the surface of whatever this is. So if you ever hear of like chromium plating, I tried to talk about that one day. Like often vehicles will chromium plate. Probably it's iron underneath, but then the iron is covered with a thin layer of chromium instead, which makes it look shiny and nice. Does that make sense? Sure, would also do that, right? Silverware. You don't make your entire silverware out of like gold. So you make it out of copper or whatever you make your silverware out of, right? But then you coat the outside layer with gold. And this is how you do this. What was that?
I said everything is a lie.
Okay, so this copper right here, yes, we made it out of copper, but to be honest, it didn't actually have to be copper probably. The point I want to make though is that this is going to increase in mass, whereas this one over here is going to decrease in mass. Does that make sense? There's a few assignment questions where it kind of comes across this topic as to this one is going to lose mass, and this one will gain mass.
The one loses, the other gains.
Yes. So here's the question I guess chemists came across is, can we predict how much mass will be gained or lost?
Yes and yes.
That's the point of today. So today's topic, now that I've done a whole bunch of before's talking, we're doing cell stoichiometry. Our goal at the end of this, pardon me, is to be able to calculate a mass of either solid that is being added to a cathode or a mass of a solid that is being subtracted from an anode. There is one question on your assignment, a few of you have been working on it with already, where I might tell you that the cathode itself is say 200 grams. My question might be, well, how much will the cathode weigh when you're done? Well, the cathode will, once it adds more, it might weigh like say 240 grams. Does that make sense? Because it's going to be more. But if we're talking about the anode, if the anode originally was 200 grams but it loses its mass, it would only weigh like say 160 grams. Because it's going to lose that mass. Does that make sense?
So if it's the anode that loses?
Typically the anode loses because the anode will go from a solid to an aqueous. And typically the cathode gains because cathodes sometimes go from aqueous to solid. That being said, there are some exceptions. Not everything goes solid to aqueous at the cathode.
I get really confused with that because, like, whenever you said it could go from aqueous to solid, but like,
Okay.
isn't the anode a solid to begin with? So how is it going from aqueous to solid?
Okay, so sorry, this one here is going aqueous to solid, which would be copper 2 plus, would pick up 2 electrons and become copper solid. So this is reduction because it's gaining electrons. So anything that reduces, most things that reduce gain extra solid to them. So therefore they gain mass. Over here, what's actually happening is your nickel solid is decaying away into nickel 2 plus and 2 electrons, thereby oxidizing and losing electrons. So this one should lose its solid mass, but this one should gain its solid mass.
Is it always going to be
So it-
equal or will it be different?
Depends on a few different factors. I would hesitate to use the word always. You guys know how I hate to say always.
We
Does
love
it-
it.
we love it. So does it gain solids from the solution in?
Yes, that's what's happening is this mass right here is losing its mass into the solution, so the watery solution will become heavier. Whereas here, this watery solution will become lighter as mass from the solution attaches itself to the actual electrode.
Okay.
So it's not so much that this guy's mass is actually being lost to here, it's more that this guy is forming stuff in there, making this heavier, and then this is actually becoming lighter, making this heavier.
Okay. So would it be incorrect to say that, well, I don't know, you just did it here for this one, but you made the mass that lost equal.
I don't think it's fair to say that it always does
Doesn't
that.
happen?
No,
Okay.
I would hesitate to do that.
So don't like, oh, it doesn't equal, so I'm wrong.
Yeah,
Okay.
because it depends on one other factor. It depends on molar mass.
Okay.
Whereas like nickel is heavier than copper, so we're going to have to account for a molar mass at some point too.
Okay.
One other thing I should point out is that not all reactions create solid stuff. What happens if we weren't using the copper reaction here? What if we were using the reaction H plus 2 electrons makes H gas? Like H2, oh my goodness. H2 gas. Would this electrode right here actually become heavier? Well, no, it's making gas. Would gas actually like permanently attach itself to an electrode? You'd get some bubbles, but it wouldn't actually make this electrode be heavier. So this works in like 95% of all cases, but just make sure you're aware that like, that's why I don't like to use the word always, there will be exceptions. So here's our goal then. Now that we've hopefully in agreement that the cathode typically gains mass and the anode typically loses mass, we want to figure out how much mass it's going to gain out of this.
You say typically, are we gonna get one thrown at us where like,
You could.
go the cat?
You could.
But none of the math changes, it's just.
No, you just need to make sure you're really paying attention.
Okay.
Okay, so let me walk you through my notes.
Back to the notes.
Back to the notes now. So after that brief, well, half-hour long intro. Well, you know what? Let's move ahead here. Let's work on this first formula. I've already mentioned the difference between voltage and current. Voltage is like more of a measure of how much energy difference there is per charge. Like I said, that's like how high up your tower is of water, if you like that analogy. The higher the tower of water, the more energy your water droplets will get as they fall. But current is like, well, how big of a hole do those water droplets have to pass through? How fast can they transfer? Right? Like if there's just a little leak in the water tower, it's going to take 10 years for the water tower to run out of water. You put a big gushing hole in the water tower, that water will be out of that tower in 5 minutes. And that's what this formula helps with. Basically, the amount of charge you have, Q is how much charge there is based on current times time. In terms of units, Q is charge. We measure charge in something called a coulomb. A coulomb. I don't know. Some of you know, some of you don't. I'll try to make sure I'm not too repetitive. A coulomb is basically a lot of electrons. Okay. There's actually a ratio to it. We did it in physics. I may as well do it again. Okay, so 1 electron is equal to 1.60 times 10 to the minus 19 coulombs. It's a physics conversion. Which means that if you want to have 1 coulomb, if you multiply by 1 electron, divide by 1.060 times 10 to the minus 19 coulombs. We did this in physics, so I know some of you guys are getting this.
Is it like 9.55 or something?
1 divided by 1.60 times 10 to the power minus 19. 1 coulomb equals 6.25 times 10 to the 18 electrons. So basically a coulomb is just a lot of electrons. Does that make sense at all? Rather than counting electrons one at a time, we count them in groups. Okay. Now, in physics, we like to talk about coulombs as a big group of electrons. But in chemistry, we already have a way of measuring a large amount of particles. And we call that a mole. You guys remember this?
Yeah.
How many particles are in a mole?
Another 6.2.
Good. 1 mole is 6.02
Times 10 to the power.
times 10 to the 23 electrons.
And so 26.
Do you guys remember this number from, like, say, grade 10? We don't really use it much. Okay. Long story short, we kind of have, like, 2 competing ways of measuring a lot of electrons. One of the ways, a very physics-based way, is measuring a coulomb of electrons. Another way of measuring electrons is a mole of electrons. Someone had to figure out a way to relate these 2 things to each other. And so there's a constant that's in your data booklet. So this one you don't have to memorize. But it's right here. It's called Faraday's constant. Faraday figured out how many coulombs there were in every mole of electrons. Which really, how he figured this out was he took these 2 numbers right here and he hopefully divided the 2 of them. So let me see how that worked actually.
It's on the second picture.
It's got to be the second divided by the first though. So it'll be 6.02 times 10 to the power 23 divided by my
Faraday's
answer.
constant. F equals 9.65.
What was that? That's the lab we're going to do on Monday.
When you calculate that.
Long story short, we need a way to find a way to convert between a physics unit of measurement of how many electrons there are, which is called a coulomb, and a chemistry unit of measurement, which is a mole. Okay. It's actually really easy to do though. Okay, I know it's like confusing stuff. I promise you this is not a hard formula. So here's the formula you guys need. This number, by the way, is in your data booklet. Here's your formula. To find the number of moles of electrons, take your current times your time. This will give you coulombs of electrons. And if you divide by Faraday's constant, it will give you moles of electrons. You don't get this formula though, so you have to memorize it.
Okay, so what? Explain it again.
Okay, so here's how this formula works. I times T is how many coulombs you have. And a coulomb is just a lot of electrons. Okay. Here's the problem though. That doesn't help us in chemistry. Because in chemistry we don't work with coulombs as like our unit of like lots of stuff. We work with moles as our unit of lots of stuff. You get what I'm saying? So that's what this Faraday's constant does, is it helps us to convert between coulombs and moles. Think of a better example here. Do you know how you measure like donuts in a dozen? And that's like a standard way of measuring donuts.
12.
What happens if I came along and came up with a new way of measuring donuts and I said, actually we're going to buy them by the shulk, and a shulk is 20 donuts? That would be kind of confusing, wouldn't it? Because you could buy donuts by the dozen, which means you're buying 12 at a time, or you could buy donuts by the shulk, which means you're buying 20 at a time. Wouldn't that get confusing? Because you wouldn't know which one of those bigger units you're ordering. It's the same thing with electrons. You don't ever have just one electron. You don't ever have like 2 electrons. You often have many electrons. So we could measure them in coulombs, which would be like measuring them in dozens. Or you could measure them in moles, which is like measuring them in shulks. What you need to do though is find a way to compare coulombs and moles. And that's what this formula does. Okay. It's actually really simple, okay? Let's try a question here. How many electrons would transfer if you operated a cell for 1.25 hours at this current?
You have to convert that into minutes.
Seconds.
Seconds, actually.
Seconds? Oh.
Because the way this works is an amp is equal to a coulomb over a second. So this thing right here needs to be in seconds.
It's 45 seconds.
1.25 hours.
So NE stands for moles of electrons. Basically, I'm asking you, how many electrons do we have total, but like as moles of it?
So what's that little note there besides your amp?
Right here?
C over
Oh,
S?
an amp is a coulomb per second.
It's a T shulk.
T? Time.
What's NE gonna be equal to that?
How many electrons move? Because current is how fast they move in coulombs per second.
Oh, we have time, okay.
And then time we have. So we know that our electrons are moving this many coulombs every second. So every second, a whole lot of electrons are moving.
So we just times the seconds by the
So what is 1.25 hours in seconds?
45 hours.
4,500?
Yes.
Thank you. So convert this guy to seconds. You see how the seconds will cancel?
Is coulombs per second the current?
Coulombs per second is your current. That's how fast electrons move through the wire. Which is kind of like the example of like, say, when they have the water, gravity water thing. If you cut a bigger hole through it, you might get more water transferring through every minute.
What
Hello.
about the F?
F is
Okay,
equal to
so then the last one here is F. It's capital F. And what Faraday's constant does is it helps us convert from coulombs, which is a physics unit, to moles, which is a chemistry unit. So we have to divide by the 9.65 times 10 to the 4, and then the units were coulombs per mole of electrons.
Times 10. Where did we get that?
This number here,
You guys skip
It's on the last page.
0.05.
and it is in your data book, by the way. You don't have to memorize that one. But you do have to memorize the formula that we're using here.
Just pretty much.
Or write it down.
1.150.
1.150 times your 4,500 has to be in seconds. Divide by this thing here. What we've now figured out is how many moles of electrons have moved, I guess, through your wire.
I thought moles was M.
N is actually moles. M is mass. What's up? She should be. She's not here today. I don't know where she is. Okay. Should be here. Diploma will be the indicator. Let's see.
Are we supposed to find it in moles, or do you want to convert it to non-moles?
No, we want to work with moles. Okay, so I got this 0.05362694
What is that? Those are moles per
Moles.
So this is how many moles of, no, not per electron, moles of electrons. So this means that you have, I mean, if you like the donuts analogy, this would be like getting 0.05 of a dozen donuts. So, I mean, do we have a full 6.02 times 10 to the 23 electrons? Well, no, but we have a lot of them still. For this first question, by the way, that's all I asked for. I wanted to know how many moles of electrons moved. Let me go back to my first picture now.
No, I didn't know who did.
What that means in this picture here is that a lot of electrons have moved from this side here to this side here. Does that make sense?
The amps is, I thought amps was just always above like 1.5.
Well, that number can change
Yeah.
because the speed at which these electrons transfer, that's variable. Is everyone with me so far? Okay. Well, if we can figure out how many electrons have moved from one side to the other, we can then figure out how much mass to either expect or how much mass to expect to have lost. And I'm going to do that in this last example. So I'm just going to do the last example and show you the last twist. So here, it's like the exact same information, only now I tell you that it's copper. And that's going to matter in a second. But like, start off doing the exact same stuff you just did. So your formula is the number of moles of electrons is your speed at which those electrons are moving, which is like a current, times the length of time it runs for, divided by Faraday's constant. So an amp is really a coulomb per second. It's like how fast all of these electrons are moving. Time has to be in seconds though. So I got 2,400 seconds. If you do that, it gets you coulombs, which is like a physics unit of how many electrons you have. We want a chemistry unit of how many electrons you have. So we're going to divide by this 9.65 times 10 to the 4 coulombs per mole of electrons. And that will now convert it to something useful for us in chemistry.
Then do we times it by moles per gram to get
In one, yeah, that's going to be the last thing we do.
get rid of moles? Oh, and then to get rid of moles, then you get grams.
Yeah, we gotta get rid of the electrons too.
I don't get that then.
Okay, so let's start with this. Is everyone okay with getting moles of electrons being 0.29844? You guys able to get that value? Yes? Okay. Okay, now comes the stoic part. We have to convert moles to grams, and that's going to involve molar mass. But we also don't want electrons anymore. We want to figure out how much solid copper to expect. Okay. So we got to do two things. One thing I have to do is times by a ratio. I don't want electrons anymore, so I'm going to put electrons on the bottom. See how these electrons here will cancel?
Mrs. Philotoff, can you please call 100?
Okay, so what am I trying to form? Am I trying to form electrons? Or am I trying to form copper?
But what's the ratio of copper
Ah.
to what?
That's where this equation comes in. Copper 2 plus needs 2 electrons to make copper solid. So for every one thing of copper solid you get, you need 2 electrons.
How do you know it's not copper 3 plus?
Because there is no copper 3+.
Oh, I thought there was.
I guess I don't have a better answer than that.
But what if it's like one that has like a double like?
You'd have to know which one you're using.
Oh, okay.
That's a good question then. Okay, so like if there is more than one charge available, you'd have to know which one you're using.
Then you multiply by
Okay, last thing, you now have moles, but we don't want moles, we want grams. So if you put moles on the bottom and grams on the top, that's a molar mass. We just need to know what copper's molar mass is.
63.55.
There you go. That'll cancel your moles away. This will have canceled your electrons away. So divide by 2 times by 63.55. You should expect 9.3 sig digs. 9.48 grams more copper.
So then,
So let's say there was
Madame
already
Doyle, can you
10
please
grams
call
of copper there.
100? Madame Doyle, please call 100.
What you might get asked then is what is the final mass when you're done? And so this is how much more copper has been added. So if there was already 10 grams there, you'd then have 19.48 grams total. That makes sense? So you gotta watch that wording carefully. We also could do this, by the way, if something was losing mass. It does it the exact same way. So you just have to be careful and figure out whether you should be adding, because it's usually at a cathode, or subtracting, because it's in an anode.
I missed what you just said.
Okay, so like when you go to a cell here, cathodes typically gain mass.
Oh, okay.
So like let's say it started at 200 grams, but then you added an extra 9 grams, you'd now be up to 209. That makes sense? But over here, if it started at 200 grams, it's going to need to lose mass. We could in theory find how much mass was lost as well.
Would it be the same?
No, not necessarily. They have different molar masses.
Oh, okay.
Does that make sense? Because in terms of things that affect this, 2 main things affect this formula. Once you get your moles of electrons, you then have to deal with your ratio. What if it's aluminum? Well, aluminum has a 3-to-1 ratio, so that would change it. What if it is silver? Silver has a 1-to-1 ratio, so that would change it. So that's one thing that could affect it. The second thing is the molar mass, because the mass difference will depend on how heavy the item is you're talking about. You guys want to try one more example and then take a break?
But the moles of electrons would just stay the same. You would use it if you were.
The moles of electrons will stay the same for both.
Okay.
Why don't we go back to this very first cell I drew then? I know it's getting to be a real mess. So the first one I drew was involving copper and nickel. So I need to tell you 2 numbers. I need to give you a current and a length of time.
I got this.
So why don't we just make up a number? Let's say the current is, let's say 2.50 amps. And then how long should we let the cell run for?
3 days.
60.
3 days, Raj says.
Oh my gosh.
Let's do 3 days.
It's like 259,000.
Sure.
So many, but I know what it is.
I'm complaining because I can't.
9,000, don't worry, I got it.
That'd be great if you did that in your head.
Okay.
So way to hell.
So for this question here, let's try to figure out how much mass we'd expect the, which one is which again? Let's figure out how much mass we expect the copper to gain, but let's also figure out how much mass we expect the nickel to lose. Okay. So I'll walk you through it if you guys don't want to move ahead. Moles of electrons will be current times time divided by Faraday's constant. And this does not matter which one we're talking about. So 2.5 coulombs per second times 259,200 seconds, divide by 9.65 times 10 to the 4 coulombs per mole of electrons. Cancel, 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 cancel.
It's a big number.
Didn't we already do the copper one?
With different numbers though. But yeah. Because we did with a different time and different current. Now we're leaving it for 3 days.
Thanks, Raj.
Thanks, Raj. Forget it over the weekend.
Did you guys get 6, 7, 9?
Yep.
5, 0, 2,
So I got 6.72
Huh?
moles of electrons.
He rounded
It's
it.
the same thing. You got 6.715, he just said 6.72.
Oh, actually, I got 6.7211199.
Oh.
Oh, I got 6.715.
I got
I'm way off then.
Is something wrong with your cool or?
9.6. Oh, I didn't do 9.65. I did 9.64.
Okay.
I'm off. Okay, so I got 6.71502.
For 72 hours.
Is it black?
Everyone get basically that number though, the 6.7, technically a 2 if you round it up.
And the unit basically is moles.
So this is moles of electrons. So now we got to use stoich. We don't want electrons. That's one step. And we don't want moles, we want grams.
Same thing that we just did.
So the exact same thing we did. We need a ratio, we need a molar mass.
We're doing nickel.
So which one should we do first?
Oh,
I mean, what?
Well, nickel or copper?
copper.
Okay, let's do copper. So we want copper solid, and it takes 2 electrons to make a copper solid. That's the first one. And then you have to times by 63.55 grams per mole.
213 from
63.
Yes.
213.
So divide that by 2 times by 63.55 means that I would expect about 213 grams more
What's a nickel?
copper.
Yeah, I got it.
So then for nickel, it should be very similar because they have similar molar masses, but it will be slightly different, isn't it? Because you'll take your 6.72 moles of electrons. It still divides by 2,
And then it's
5869.
58.69.
So that means it loses 197
Yes.
grams.
So that means that that original piece of metal there must be at least that much, otherwise the cell is going to die.
Oh, because we know there's that cast.
Divide by 2 times by 58.69. So I got 197. And so this would be less of nickel.
This ain't that bad.
If you were doing the difference. Or
What was that?
If you were doing the final thing.
Okay, so then let's go back to my picture here. So let's say we started with 200 right here. You'd be down to 3 grams, right? Whereas this one over here, if you started at 200, you'd then be up to 400 and whatever it was.
13 or something.
Does that make sense? One last thought here then. Why does a battery die?
You run out of stuff.
You run out of stuff. As soon as this thing, you run out of it, the battery's dead. That's why a battery stops if it's a primary cell. There is one more thing that could stop the cell, by the way. This solution right here is the thing that's like making this thing gain more mass to it. If this solution runs out as well, you also could have your battery stop.
Could the potassium become solid by any chance?
No, because they're way too low on the table, I think. Because it wouldn't react spontaneously with nickel then.
Right.
Does that make sense?
Yeah, it's way below.
Because that's the whole point, is that potassium is so low that it shouldn't ever react.
That's right.
They won't last here.
What about in the secondary cell?
So in the secondary cell, then once your battery is dead, and so this thing is fully decayed and this thing is really big, then you change this from like your iPod to plugging it into the wall. So you make it a battery with like a plus and a minus. And then you force the electrons to go back the other way, meaning that all of this nickel that was in the solution reattaches itself and the electrode gets bigger again. And all of this extra mass right here redissolves back into here again.
So you could go like, how do you have like a copper coating and then it like goes back?
Sure. So then all of this copper coating would then go back again. So again, this didn't actually have to be copper right here. This thing could have been platinum or something for all we care.
And it's not the copper solid that's reacting.
It's not the copper solid that's reacting, it's just forming more copper solid from the Cu2 plus that's in the solution. Okay, summary, then we'll take a break. So in terms of this section here, there's just one formula you need to know. You're going to do it once on the diploma, probably. Maybe you won't even have to do it. But they don't give you that formula. So you have to be able to memorize it's I times T over moles of electrons. I times T over Faraday's constant. That gives you moles of electrons. Once you have that moles of electrons, divide by the ratio, which is often it's 2, but it doesn't have to be 2. Like aluminum is 3, silver is 1. And then last step, times by molar mass. Don't mess up the adding or subtracting because a cathode usually gets more mass and an anode usually gets less mass. I use the word usually because that's not always true.
But we'll be able to
So
tell
if
when
it just goes
it's.
from solid to aqueous, it's losing, and if it goes from liquid to solid, it's
Yes.
gaining.
Does that work?
Yes.
Okay.
How do we know if it goes from solid to aqueous?
Your book.
Look at your book.
Oh.
What we're on to say, the yearbook.
Yearbook.
That will tell you too. Okay, go take a break. We're done.